is Jakub, just as Malte said, and today I'm going to present the topic of Voxels rendering with JavaScript. Just a short about me, I just started JavaScript like in December, so before I was formerly a Python developer. So that's my first attempt to ever do anything in 3D, so just take it into account. My Twitter is Sasquatch, and GitHub account is rather empty currently, but I will place the code after my presentation. And that's the blog, also mainly about Python currently, but I'll try to fix that in the upcoming weeks. So, why Voxels and octrees? Well, basically, because of this guy. Everybody knows the guy, I believe. It's John Carmack, the guy behind Doom, Wolfenstein, Quake, and the games like that. So the godfather of gaming, okay? And just about 2 years ago, John Carmack said that we are currently reaching the limits of the possibilities to render render graphics using the traditional methods. So, what are the traditional methods? Well, obviously, traditional methods are rendering using polygons, which are just tiny triangles. And polygons are cool because this hardware is optimized to render using polygons. Also, polygons are really nice to show uniform surfaces, but they suck at complicated scenes. So Carmack decided to go a bit different way, and he introduced voxels. Well, not introduced, but he said in the next engine he's gonna render the scenes using voxels and octrees. So voxels are just small cubes, so we just move the pixel in 3D dimension, creating a tiny cube, so you can get a better representation of the scene. There are a lot of pros with this technique. Implementation is really straightforward. Traversing the octrees is really easy. Collisions are easy. Resolution change is easy. We have a possibility to generate sparse voxel octrees, so the nodes of our tree that don't contain data that need to be rendered are just not shown. It's really easy to hide surfaces that we're not showing. There are many possibilities to improve because the topic is not as much researched as polygon generation, but there are a lot of cons. Traversing tree can be expensive because if you start from the not from the correct point, you just can move back and forth across your tree, and this can be really expensive and time-consuming. Animations suck. Well, just think about moving 5 million or 50 million of atoms at a time across the tree structure. It really sucks at the moment, but we'll check about that later. And size does matter. Unfortunately, storing data in a knock tree for voxel is really size-consuming. So let's proceed. So first we'll dig into octrees. Basically, octrees are just a tree data representation which divides the spatial into small blocks, when each block consists of 8 children and so on and so on and so on. This is how it looks basically, so pretty straightforward, I believe. Everybody can get it. And how I implemented it? Well, to be honest, I just went through like thousands of different codes, thousands of different implementations in C, in JavaScript. There is, I believe, only one implementation in JavaScript, but I wasn't able to contact the author, so I'm not sure how it works. He just states that it does. After that, I went to check the implementations of quad trees, basically just the same idea, yeah? But still, I wasn't able to find anything interesting in there. So, after skimming through some C code, C++ code, I was able to come up with a solution, of my own solution, which is not overcomplicated and it works. So, basically, that's the octree object. As you can see, we have the node, which is the root of our tree structure. The root can contain shape if we just have one level. We have also a position of a root. We have also type which is, I believe, not useful here. Okay, maybe it is. The length of the wall, which gives us the size of the whole space, and the depth and the max depth, which are useful when traversing, when adding, and etc., etc. So, following, now the node. The node basically is just the same. It differs with having a nodes reference, which is a reference to an array that contains the child nodes of the root, of the node, which can be either another node or can be the stuff that we will be rendering during our scene. And the data that will be rendered are just stored in a flat array, because it's faster to traverse through flat array than going through the whole tree. It also has a parent reference, because it's faster to, it gives us really a boost when traversing through our tree. And location, which is the real magic here, the real deal. Okay, now location. I needed a way to find find the node I'm currently dealing with across the whole structure, and it had to be fixed, because basically we don't want to guess in which node we are. So I went the bitwise-like idea, where the node, the position of the node inside the parent node is just defined by a difference on x, y, and z axis. So if the node is farther than half of the length of x, y, or z axis, we just set the bit to 1. And if it's closer to 0.00, we just set the bit to 0. This gives us a uniform distribution. It's the same across all the nodes, so we just take it for granted. Now, here's the rest of the location magic. I'm not really going into the bitwise way, because bits kind of suck. And so I decided to just set the position and save the position as a string, as a triple of chars. So just traversing deeper into the tree, I just add the current position of my node inside the parent node. So you just, as you can see, if the node is, for example, the first node in the array, then the second node we just start with a 0, 0, 0, and so on and so on. We just go deeper and deeper and deeper. And finally, adding the triples of strings, we just end with the correct position of our node inside the whole octree. Now, some code for, really, it's not maybe too obvious, but I really try to keep it simple. The recursive adding, of course, there are different approaches, but the recursion is the easiest to just show to you. So we just traverse across the octree. We have two, as you can see here, current location is not equal string location, and current depth is not equal string depth. So these are the two operations that limit us across the traversing. So for example, for 8 level tree, unless the current location is equal to 8 times 11111, we just traverse deeper and deeper. If the current depth is not equal desired depth, we just go and add our node in the correct way. So how the function for inserting looks like? Well, it's pretty straightforward. We just divide the string of location into triples once again, and just following the idea I told you about before, we just select the correct. We just first of course we need to recalculate the position from string to integer, from bitwise to integer. Then we can go through the nodes, selecting each node, and when we're done, we just add the node, set the values, and that's all. So the last interesting function here is for retrieving the node. We also use recursion here, and we can make the usage of the bitwise notation. So we just calculate the boundaries of the node we're currently in, as well as the node point or object we'll be matching against. And if the x-axis, if the x position keeps in the boundaries of the node we're currently in. We just select the node. And now we can use the magic I told you about, because if the position of the object we're matching against the node is smaller than the half of the length of, for example, of x-axis or y-axis or z-axis, we just set the bit to 0. Either way, we set it to 1, and this way we can limit the amount of the child nodes that we need to traverse, so we can really boost up the search. Now for some real-life usage. I will just show you 2 examples. The first one, raycasting. Also, I believe that this graphic shows it all. We just need to calculate the position on the entrance and the position on the exit. And then we traverse across the ray through our op tree, and we select only the nodes that were affected. We just skip the rest, and we select the nodes that were inside the first room, and that's basically all. The second one is collisions. The simple bounding boxes approach is the one I've told you about, the one that uses the function presented earlier. But the other one is a bit more complicated. So, basing on the path that our object already traversed, if it did, we can predict the road it will follow, calculate the bounding boxes of this element, fire rays from the edges of the bounding box, and this also selects us just the space that will be affected and the space that we need to really take care of. That's just a simple demo. I hope that it will work, because this iframe is a bit more not cooperating, to be honest. Okay. Yeah, okay. So just a simple collision on bounding boxes. We just move here, and voila, okay, we have a collision. So pretty cool. Thanks. Okay, nearly half of the time. Okay, so now, first, voxels. Voxel, as just I said previously, it just, we move pixel in 3 dimension, we create a little cube from it, and basically that's what we create a world from. The usages of the voxels, well, you might have thought that they are not used at all because the cons I've said previously, but, well, they are. We use them, for example, for medicine, for rendering 2D images, as well as we use them, they were previously used in games, like Blade Runner, the whole game engine was created using voxels. Unfortunately, they had some problems with the efficiency of this engine, I believe. In Command & Conquer and Red Alert games, the units in the game were created using voxels. The Outcast game, the whole map was rendered using voxel, but they were cheating a bit. There is a game called Voxelstein, so a clone of Wolfenstein. Pretty cool. Also, the whole world is created of voxels. You can just see it clearly here. And just recently, there was a lot of noise about technology called unlimited detail technology. Well, they really didn't release any official info about the technology behind this demo. But Notch, the creator of Minecraft, and some other smart guys, stated and agreed that they for sure must be using octrees and voxels because they're mentioning atoms for the rendering of the world, so atom and cube, yeah, that's the same. As well as the models shown during the demo are just all the same, so that's easy to just cut part of our octree and duplicate it. And so basically that's it. Also, yeah, for sure, we'll see it in Quake 5 and Doom 4 and whatever. Other implementation. I just found one implementation of voxels using JavaScript, which is the one displayed here from a guy called Onaluf. Why we don't like it and why that's not what I wanted to do? Well, basically that's not a 3D engine, but 2.5D. We don't have the freedom of movement here. We just can move. Sorry. Yeah, as you can see, you can just move in this way. Also, it uses height maps only. It doesn't really have a structure, so you cannot have overlapping pixels when there is a free space between them. So, well, that's not all. That's not what I wanted to build. Now, short about my engine. It's a pre-beta alpha, really. I just can't even say how not finished it is. There's still a lot of work to do. but basically I'll be able to show you just a working demo. It uses Michal camera type, thanks Marius Gunnarsson for it, the creator of Origami 3D. I use GL matrix for calculating the matrix operation. I'm using quads instead of triangles for rendering and texturing, because apparently drawing a quad, it just uses 4 moves, and drawing a quad during using triangles needs 5 moves, so we just have 1 additional 3. I use sparse voxel log trees, so the space that doesn't contain any data needed for rendering is just removed from the tree. There is a backface culling, there is no raycasting, so it really affects the performance. And still a lot of things to be done, so I believe that somebody will help me after the conference with finishing this. Whoa, sorry, once again. Of course, we need some data to generate our world, so I went the noise generation way, and I'm using Perlin noise for this. Perlin noise for the win, yeah. Perlin noise, what is that? It's just a set of formulas, mathematical formulas that Ken Perlin, I believe, invented it in like 1980s. And that's a really smart guy, because basically everybody uses that, even unwittingly. And the guy got an Oscar for Tron special effects, yeah, so that speaks for itself. Also, the effect is used in Photoshop cloud filter, so probably some of you have used it already. He has a site that describes step by step how the noise is made and how to implement it, I believe, in C. So probably maybe somebody will find it useful. Basically, that's the noise I'm generating. So that's the sample 256 for 256. So you can just generate it differently. Wow, yeah. I'm just using some anti-aliasing on it and some different calculations just to fit it to my word generating engine. I was thinking about going the Minecraft way, when they just generate few noises one after each other, just splitting the whole generated noise into small pieces, taking this piece, generating noise over this piece, and so on and so on and so on, and it just gives them proper results. But I didn't need that, so how we do it? We just create an image data array, the size of canvas pixels multiplied by 4, of course, because RGB and A. And for each pixel, we just null the RGB data to, we just set the RGB data to 0, and use Perlin noise only to generate alpha, and because it just gives us a uniform distribution and really it works properly. So then we just have the smoothing a bit, read the data from the created image, cut the noise in half, because obviously we don't want we're not in Himalayas, we don't want the noise to be the size over the whole generated world, and then just render it. So how it looks rendered? Well, basically something like that. It's pretty simple currently. As you can see there, it resembles some kind of world, not sure which. And just, okay, now a demo, short one. So now a demo of generated Perlin noise, a small sample because the performance is really poor. I mean really poor. Because as you can see, I've added some lighting. It's just a work from last day. So basically you can see that it's working. Hopefully I'll manage to just improve it a bit and have it work better. And now the fun part, we need to generate the world, but I just hope that my Firefox won't die, because really it's time consuming and really resource consuming, and I will just tell you in a second why. Yeah, as you can see, it almost dies. Yeah, still calculating, yeah. Yeah, oh, free me, yeah. Why it takes so much time? Well, basically I'm generating a sample of 64 by 64 by 64, so you can calculate how much voxel we have in it. I haven't yet implemented any removing of the hidden voxels that are not seen. So the amount of data that need to be rendered, as you can see, is just really big. And you can see the noise generated in the corner. Basically, it resembles a bit the thing that is generated. I will just try to move it, but I just said it's really poor performance. There is also zooming, but I'm not sure if it's capable of showing it. Wait, okay, I have 10 more minutes. Yeah, well, it resembles Minecraft a bit. Even the textures I used from Minecraft. So I needed to really turn off the lighting because the computer would die even that it has 4 cores. And well, basically, why it's working this way, why the performance is so poor. Oh, even closing of the tab is really time consuming. Oh, come on, come on, come on. How are you playing? Yeah? Thanks. I just really need to show my slides again. Yeah, everybody's seen it. Ah, sorry for that. It shouldn't take so much time. Oh, come on, Firefox. Oh, something strange happened. I believe I just turned the world upside down. Okay. Oh no. This really shouldn't happen. Oh, no, it should. That's how it's meant to work. Yeah, I just need to consume the time a bit. Yeah, cool word. Okay, I just believe that I have to. Come on, the slides. Okay. Sorry, I just need to buy a MacBook, I believe. Okay, kill this process. Yeah, close the process. Yeah, Firefox is checking for a solution. Yeah, for sure. Okay, so it even fixed it. Okay, so where are the slides? Why it's not working? Sorry for that, really. You just can get a bit bored. Maybe I'll tell a joke. Oh no, it's working. Okay. Yeah, so it was like 26, I believe. Oh yeah, basically we're here. Yeah, I can trust Parolin. Yeah, the noise. Possible improvements. Why is working so slow? Well, there are a lot of things to be done, as I said earlier. We can join smaller voxels in big ones, so we just have less data to draw. We need to hide unseen voxels, like surrounded by other voxels. We can draw the whole images with image data, so just the way I used for generating the noise, we can use it the opposite way. We can create, maybe not the opposite way, we can create our image data array, but without nulling the RGB. And this gives us a boost of like 4 times, so it's really cool. Proper recasting needs to be implemented. Yeah, and maybe some other traversing algorithm, as well as WebGL, because currently I haven't used WebGL because WebGL is cheating. And why is that? Basically, WebGL, OpenGL, and other libs for graphics just don't allow you to create voxels. You're just forced to use polygons. So basically, building a world of voxels with WebGL is just building a world from polygons. So you can implement it easily. I've tried implementing it using the FreeJS, so it's just straightforward, because even Mr. Dupe created a demo of building a world of voxels, so it works. And to summarize, well, drawing voxels is slow, really. It's slow. Everybody says that it's slow. Animating is slow. Size is an issue. And it really seems impossible right now. Well, John Carmack states that he was able to animate like 3 million voxels, but nobody believes him. So probably we should wait for him to finish his engine. But still, oh, that's the cool quote I got from, I believe, last week. We have to everybody said that there is nothing faster than speed of light. Well, Neutrino just proved that they were wrong. So maybe the same will work with voxels. Just a bit more info. You can ask me about the Voxels. You can check the GitHub after the presentation. You can come to voxelsblogspot.com, which is a blog of guys from NVIDIA, which use CUDA for rendering the proper voxel images, which work. And you can also ask just Carmack how he did it, but I'm not sure if he'll tell you. Just a short demo, how it should be done. I believe that. Okay. So as you will be able to see, yeah, it's pretty cool. So they have potential for sure. The world looks cool. So probably with some help from you guys, or with some help from other guys that will just dig deeper into this topic, there will be a possibility to create such things with JavaScript. And if I close that, once again, you don't want to cooperate with me. Okay? Just let's demo, because you obviously can go deeper into this topic or just say it was all bullshit. So instead of going deeper into voxels, you can just no, it's not working. Yeah. Instead of going deeper into voxels, you can just play Imperial March using floppy music. So, thanks. That's all. So,
questions?
Yeah, if you have any questions. No. Chrome dies, Opera dies, Internet Explorer doesn't really show the window, so I believe that Firefox is currently the only browser capable of displaying this data, because it's about 250 megabytes to show in one rendering, so that's really a lot of data to be shown. That's the problem.
Great, thank you.
Thanks.